We do the calculus in hockey. I'm Maddie.
And I'm Hannah.
In the presentation, we're going to discuss, obviously, like the what and why we chose hockey, volume of a puck in different ways, comparing the speeds of skaters, because like with velocity and acceleration and stuff, as well as arc velocity and acceleration when swinging a hockey stick, also the area under a lifted puck, and then when there's a goal, like a goalie like trying to protect the goal, how the distance changes between the skater coming at him and the goalie protecting the goal.
Okay, so why we chose hockey is because I've been playing hockey for 9 years, and it's a game of changes of velocities and areas. There are different volumes in a lot of ways, and it overall has a lot of different factors that make it unique, and we wanted to investigate these factors. Maddie also plays soccer, and it's very similar in terms of rules and the layout of the game. Okay, so a little bit of history on hockey. It has come from a lot of different origins, such as Iceland, Russia, England, Sweden, but originally it came from Montreal, Canada. The first organized game was on March 3rd of 1875, and it consisted of 2 9-player teams. At first it only used a ball, or so-called a bum, but at this point they made it into a circular piece of wood, but today it is a circular piece of rubber. The goalposts were only 8 feet apart, and today they're 6 feet wide. The sport began to grow, and more teams were relevant enough to hold the very first World Championship of ice hockey in Montreal during their Winter Carnival in 1883. And now to the calculus. Okay, so what we wanted to do was compare cross sections and disc rotation to find the volume of a puck. And so originally I thought it would be very difficult to find the different equations, but as I worked through them, we ended up finding the integrals, and the graph may look a bit different, but the equation was very similar, and we found the volume as 7.0685 inches cubic.
Okay, so as far as skating speeds, we didn't use velocity because speed would stay the same, but velocity will be negative if you're going in a negative direction. We just wanted to focus on the positive part of when this is Connor McDavid, and he's like, I think he holds the record right now for fastest like lap around a hockey rink, and those were 3 of his top times that we just found on like Wikipedia, and those are just the times for 1 lap, but like I couldn't find anywhere what a lap was, like how long it was, so I had to look up how many laps there were in a mile. There's 11 laps in a mile, and then 5,280 feet in a mile, so I could like divide those and get 480 feet in 1 lap, but we wanted it in meters per second, so I just like used a converter and got it into 146.304 meters. So then using the equation, or like the formula, velocity equals distance over time, we used the 480 feet and divided it by his fastest time. We just wanted to focus on his fastest time because like that's the record right now, so focusing on that would be the biggest velocity or speed. So that ended up being 36.060 feet per second, and when converted into meters per second, which is more common, like universally, it was 10.992 meters per second. And what was like interesting with his skating is like he was skating around the rink, but at his starting point he wasn't stopped. So like he had no acceleration because he started at his like average speed of 10.992 meters per second, which is why his time is so low. So yeah. Continuing with that, this is Kendall Schofield, and she holds the women's record right now, I think, for fastest lap from stop. You're doing it. So it does it twice, it like replays it, and the first time it just shows her skating around. This is her time down here. and she just has to cross that line again. And then the second time it'll play, it'll have a little like number above her head, which is her speed in meters per second. I don't know if you'll be able to see it. It's like this tiny little number under there. So it hovered right around 20 miles per hour. So once I had the 20 miles per hour, and I knew that I looked, her meters per second was like 8.941 meters per second. So using that same equation, I could find her velocity again, like in a different way, because I used the same meters as before, and then that was her time, 14.346 seconds. And then also I want to find her acceleration, because since she started from a stop, like with 0 meters per second, I could take the amount of time it took her to get 8.941, okay, 8.941 meters per second, and I looked at the video, and it said it took 4 seconds for her to get to that velocity. Since, that was 20 miles per hour is 8.941 meters per second. So it took 4 seconds to get to that point, so then by dividing those, I could get an acceleration of 2.235 meters per second. Okay, so going back to like the lap skating, this is the rink dimensions that I used. This should be the universal dimensions. And it was weird because it like measured like interesting distances, so I kind of had to just like divide this in half and then add it to this to get the distance from like the center to the goal line. And then if you click again, it'll go 26.5 meters long from the halfway point to the goal line. And I wanted to calculate the area inside, and this was only half of the rink. And then I had to plot all these points on my calculator, because this is what like half a rink will look like. And so I was just calculating the area inside of half of the rink, because I wanted to find out how much distance the skaters would cover in a lap. And I took the 26.5 meters long from half to goal line, and I was just going to do it like geometrically and solve them individually, since it's like curved edges and stuff. So 30 meters wide was how wide it was across, but I decided that like you don't skate right on the boards, so you'd skate about 1 meter in, and which you could see in the other video, she wasn't like right on the edge. So then I just subtracted 1 meter from both sides and made it 28 meters wide was the area she covered, or both of them covered, and then multiplied that by the 26.5, which was halfway to the goal line, and got 742 meters squared. And then the end over here, so it was like the goal line to the end board, was it had a 4 meter distance here, and then 24 across. So when I multiplied 3 minus 1 for the 1 meter skated in, I got 72 meters squared. And then the corners, I decided they were going to be like quarter circles. So those had a radius of 4, and then skating 1 meter in is 3. So then when I did area of the circle, I found that the 2 corners combined were 14.137 meters squared. When all 3 of those calculations were added together, it was 828.137 meters squared, which was still only half. So then I multiplied by 2 to get the whole rink distance she covered, which should be like the most accurate. And then when I plotted the points, and I tried to find the line
At this
of best
time,
fit.
all juniors are to be released for locker cleanout. Again, at this time, juniors may be released for locker cleanout.
When I
Thank
plotted
you.
the points, I was trying to find the line of best fit, but like obviously that doesn't fit super great. But the parabola I thought was like the most efficient way to like signify the route that the skaters took. So when I integrated that, I ended up getting pretty similar, but not quite. 786.389 meters squared, and then that's still half. So then multiplied by 2 would be the 1,572.779 meters squared, which are like pretty similar. Okay, so then I did arc velocities and acceleration when I swung a hockey stick, but obviously it was not a great video because I'm not a hockey player. So when I did it, like as you can see, it like, I slowed down here, which you're not supposed to do, but I was like afraid of hitting the ground, so my video is not 100% accurate because I'm not a pro. So in this video like has a better viewpoint of it, of what it should look like. So this is like an actual hockey player swinging a stick at the puck, and like it'll show that once you get to the end, your velocity like keeps going. You're not supposed to like stop. Yeah. And then on the next slide, I did, I put it in the capstone and found the, it was really weird because I found the position of the hockey stick, the end of the hockey stick, versus like the origin, which is like the middle of me. And then this was like the radius between me and the end of the hockey stick, which was pretty constant, which makes sense since I was swinging it in like a circle. And then when calculated out, the arc length went up, and then the arc angle of the video also like looks the exact same. And then when I found these two lines of best fit and took the derivative of them, and then I plugged them into my calculator, they also, like, these are the derivatives, so then since these are position, those are velocity. It was linear velocity versus angular velocity, and I should have just done a picture of like the first quadrant because that's all that like really mattered in this one since time can't be negative. But like if you zoomed in on just the first quadrant, they would look pretty much the same, and it would show that like my velocity decreased as I went towards the ground, which is not really supposed to be it, but it was like comparing that between how pros would like keep swinging all the way through.
Okay, so next we found the area under a lifted puck, and because we didn't have ice or a puck, we took a video using a practice ball. And that's a curve. So we plotted the points in capstone, and we found a line of best fit, which was a quadratic, which was y equals negative 0.18 x squared plus 1.74x minus 1.99. And so we integrated that on our graph from 1.212 to 8.333 because that was where it was on the ground on our capstone. And the area came to 10.352 meters squared. And so we took the derivative of that to find the velocity of it, which is y equals negative 0.36x plus 1.74, and it was equal to 0 at 4.833 seconds. So that was the time that it reached its highest point, so we plugged it into the original function and came to 2.15 meters, which was the highest point that I would lift the practice ball. And so next we calculated the distance between the player and the goalie on the breakaway, which even though this is a slow clip because it was a practice clip, it still would be the same rate as it changes, so it would still be very similar. And we found a linear equation, which was 1.78x minus 9.84. We realized that it was a negative function, but if we took the absolute value of it, it would show that distance decreases, and the reason for that is because when we plotted them on capstone, the first object was further